This is a video covering a challenge problem discussed in supplemental instruction for pre-calculus. It's a hard problem, but it does encapsulate a lot of the topics I think we've been going over in chapter 3 and some stuff from chapter 2 as well. So it's a really good problem to sort of test your skills built up over the last two chapters. And so I wanted to make a video so you guys can watch it over and, feel free to speed up the video if I'm going too slow or slow it down if I'm going too fast. So let's jump into this problem real quick. Let me just like box this off. Okay, so there's a lot going on here to start, but you want to keep in mind of a special rule. And so the rule that's often discussed, and let me do it in a different color so it can stand out a bit. Um, if you have something like x to the negative a, this is the same thing as saying 1 over x to the a. And so these parenthesis things we have going on in our problem, they look intimidating, but the first thing that you can do is just go through and simplify this problem into something we're a little more used to. So to get started, I'm going to rewrite this section where it has x minus 1 to the power of negative 1. In each of those instances, I'm going to rewrite the problem. So it's going to be 2x plus, and then this is going to be 6 times 1 over x to the minus 1 using the rule that we just discussed. And then I'm going to get greater or equal to 11 minus 8 times 1 over x plus 1. I'm going to take this one step further by distributing my 6 and my 8 out through those fractions. So I would get, start over here, 2x plus 6 over x minus 1 to the power, or sorry, not to the power, is greater or equal to 11 minus 8 over x plus 1. Okay, so now we've sort of taken this confusing looking problem, and while it still looks intimidating, we've sort of brought it into something we can understand. So the next thing we want to do is we want to get rid of these fractions because these fractions are going to make it very difficult to solve this problem. And before I actually do that, I'm going to shift everything over to one side so that the computations are a little easier. So first thing I'm going to do is I'm going to move this 11 over. So 2x minus 11. And I'm going to move this 8x term, or 8 over x term over. So this will be, I'm going to order it a little weird. I'm going to put the 6x minus 1 first, plus 8 to the x plus 1. So as you can see, what's left over on the other side is 0. So I've essentially taken this 11, put it right here, and this 8x term, and put it here. And now I have a whole chunk of terms, but it's all on one side. And so I can start manipulating this in all in one place. And so the next thing I want to do is I do want to get rid of these fractions. And so I noticed that I need to find a common denominator, or not a common denominator, but I need something that will cancel both of these fractions. And so the way I can find that is I can actually do x minus 1 times x plus 1, and this will get me x squared minus 1. And so if I multiply everything by this term right here, it's going to cancel this, and it's going to cancel this. And so if I were to multiply this entire equation by x squared minus 1, you can see that the 0 is just going to stay 0. Nothing's going to change here. And the, if I can scroll down a little bit, the rest of it is going to get its own term of x squared minus 1. And right before I do that, I'm going to add these parentheses right here just to sort of make the simplification not as nasty. And so if I go ahead and distribute this term to everything, I'll get 2x minus 11 times x squared minus 1 plus, and then keep in mind that this term, this x squared minus 1, is the same thing as x minus 1 times x plus 1. And so when I multiply this by something like 6 over x minus 1, this term will cancel with this term, and we're just left with 6 times x plus 1. So this is 6 times x plus 1, and the other term is going to cancel, so I have 8 times x minus 1. And then again, that 0 is not affected. Okay, so now we've rearranged the problem into something that makes more sense. We've eliminated the fractions. It's time to start combining like terms. And so I need to multiply out this part. So I'll get 2x to the third. I'm going to multiply the outside minus 2x, multiply the insides minus 11x squared, multiply the last ones times or plus 11. Then the 6 is going to distribute plus 6x plus 6. The 8 will distribute plus 8x minus 8, all greater than 0. And so now that I've done all of this, I can go ahead and actually combine my like terms. So real quick, I'm going to sort of highlight the things that I'm going to combine just to make it easier on myself. So those are all my x terms. Here are my constant terms. And then the cubic term and the quadratic term are just singular, so I'm going to leave those out. So I will get 2x to the third minus 11x squared. Then I'm going to be combining a negative 2, an 11, and an 8. And so let's see, what will that be? We will have, oh, sorry, not an 11. A negative 2, a 6, and an 8. I was confusing myself there for a second. So we're going to have the 8 and the negative 2 will combine to be 6. 6 plus 6 is 12, so plus 12x. And then we're combining an 11, a 6, and a negative 8. So 6 and negative 8 is negative 2. 11 minus 2 is 9, so I get plus 9. All greater than 0. Greater than or equal to 0. Okay, so at this point, I now have a third degree polynomial that I need to factor because I want to know where is this going to be greater than 0. And so I have to make a sign diagram for this function. I cannot make an accurate sign diagram unless I go ahead and actually factor this out. And there's no way to factor this without brute force. And this is what makes this problem really challenging, is because, you know, this is something that by the time you're working with rational functions, it's really easy to forget how to do these higher degree factorizations. But let's go through it. So the first thing we have to do is you have to use the PQ method to test some zeros. So let's do this in a different color so it stands out a little bit. So I'm going to make some space. All right. So we have Q is 2 and P is 9. And I need to know the factors of each of these numbers. So the factors of 2 are just 1 and 2, and the factors of 9 are 1, 3, and 9. And now I can take these numbers and put them in the format of plus or minus P over Q. And I think that's enough colorization for now. Let's switch back. And so this is going to be all the combinations I can make with 1, 3, 9 over 1 and 2. And so in total, we can just do the, combine the ones. So 1 over 1 is 1, 3 over 1 is 3, 9 over 1 is 9. Then we're going to get 1 half, 3 halves, and 9 halves. And so this is our list of potential zeros for this function. And so if I was actually going to go through and solve this, I would need to start testing a lot of these. I am not going to make you sit through me solving every single one of these possible zeros. I do know the answer, so I'm going to pick the ones that work just for the sake of time. So let's just say I am extremely lucky and I decide to guess negative 3. And so what I want to do is I want to synthetically divide negative 3 by my original polynomial. So I have 2, negative 11, positive 12, and positive 9. And so let's do synthetic division. Bring the 2 down. Negative 3 times 2, that is negative 6. Add those together. I'm getting negative... what, did I do something wrong? No, I'm so sorry. This is supposed to be positive 3. That is my mistake. Positive 3. We get a positive 6 here. This becomes negative 5. 3 times negative 5 is negative 15. This is negative 3, negative 9. And because I have a 0 here, I know that this is a factor. However, we actually are not done yet because you want to test these things twice. So this is the term I get right now, but I want to do it again. Bring the 2 down. That is 6, negative 1. Sorry, it's positive 1, not negative 1. 1. 3 times 1 is 3, and 0. So what this tells me is that this term right here, 2x plus 1, has multiplicity 2. Or sorry, not that, but that term doesn't matter. The 0 is x equals 3, and this has multiplicity, should be an L in there, of 2. So we're going to box that in. And let's say I get extremely lucky and I happen to guess the other correct 0, which should be, hopefully I can guess the right one, even though this is a pre-planned guess, of negative 1/2. And so again, 2, negative 11, 12, 9. Bring the 2 down. 2 times negative 1/2 is just negative 1. Add those together, you get negative 12. 12 times negative 1/2 is just 6. And then 12 plus 6 is 18. 18 divided by negative 2 is going to be negative 9. Add those together and get 0. You would want to test this again, but I will let you in on a little secret that this has multiplicity 1. Don't want to spend too much time doing this. So this is x equals negative 1/2. Multiplicity equals 1. Okay, so with this in mind, I can now create a factored form of this function. So I know I will have x minus 3, remember, because x equals 3 is the 0, and its multiplicity is 2, so that's a squared term. I also have x equals negative 1/2, and so I can actually write that like this, because remember, you want it to be so that when you solve these terms for 0, you're getting back your 0. So just to show, for example, if I set that equal to 0, I get x equals negative 1/2, and that matches what I found. So that's kind of how I'm building those terms. And that has multiplicity 1, so we are just going to leave that alone. And then keep in mind that this is still greater than or equal to 0. Okay, now what's our next step? Well, we need to know when this function is greater than 0 and when it's less than 0. So I found a couple of things. I know the zeros, so actually real quick, I'm going to, let's bring the original function back down just so we know what we're working with. I'm going to copy and paste this. Copy you. Come on. Paste. Okay. So remember what we need to know for a sign diagram. We need to know, first of all, the zeros. So zeros are 3 and negative 1/2. But we also want to know where this function is undefined. This is probably the trickiest part of the problem because we haven't done the session yet in person, but I feel like at the time of recording this, sorry, if you're watching this video, you've probably gone to the session, but as recording this, I haven't seen it yet. My guess is that most students would miss this part. You also need to include spaces where this function is undefined. So like vertical asymptotes / zeros / undefined. Don't really know a good word for this, but and you might be looking at this function here and saying, what are you talking about? That is defined for all numbers. Yes, but remember, that is not our original function. If we scroll back up, if my sweaty fingers can do the touchscreen correctly, if we scroll back up, you'll actually see that there are 2 fractions that can cause a value to go undefined. And that is, let's do it in red, x minus 1 and x plus 1. So there is an undefined area, plus or minus 1, in these 2 spots. So whenever I'm going through and doing my sign diagram, I have to include those points as well. And that can really trip people up. So let's leave a little more room for this sign diagram. So negative 1 and positive 1. And so when I make this sign diagram, I need to include all of those points. So we've got negative 1, we've got negative 1/2, we've got positive 1, and we have 3. Now at this point, you can use whatever method you like of doing sign diagrams. I'm going to use the arrow method that was developed by Dr. Bosco, the coordinator of Math 1300. If you are unfamiliar with this method, it'll look a little strange, but don't worry, you can always use your own method to do this. So the -1 comes from a linear term that is positive. The -1/2 comes from a linear term, which is positive. The +1, again, linear positive. And that 3, it does have a multiplicity too, so it's going to come from a quadratic term. You technically don't need to draw quadratics that are positive when doing this because they won't affect anything because they're always positive. But I like to do it. I like to see what's going on. All right, so now let's count up our negative and positive values for each part of this sign diagram. So at this section right here, we've got a negative, 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 and a positive. 2 of those negatives cancel to a positive, but 1's left over, so this is negative. Then I have a positive, 2 negatives, and a positive, and those negatives will cancel to a positive. Then I have 3 positives and a negative, so that's going to be negative. Then I have all positives and all positives. And so our sign diagram is going to look like this. And so when I am writing out the interval notation, I want to, here, I'm gonna write it up here so we can keep everything in one spot. So I see that my symbol is greater than or equal to 0. So I want to know when things are positive or equal to 0. And so what I can do is see that starting at -1, going up to -1/2, this function is greater than 0. Now keep in mind, -1/2 is a 0 of the function. We've established this right here. So that can have a closed bracket because that function is allowed to exist in the domain of the function. Then I'm going to put a union, and then starting back up at +1, this space down here, I'm going to make a new interval, but keep in mind, 1 was our value that was undefined. So this needs a parenthesis because 1 is not allowed in the domain. If I try and use the number 1, remember, according to those fractions I showed you at the top of the page, it's going to be undefined. So that's a closed parenthesis. And then don't make the mistake of stopping at 3 because everything past here is also positive. And so it goes all the way out to infinity. And so that's how you would solve this problem. It's a bit of a long process, but using all of those steps, all those things we've covered, you can get to a final interval notation of this. And so remember, what this answer is telling you is that if you pick any value within those intervals and you put it through the original function, which is up at the top, you will get a value that is a true statement according to this operator. So thank you for watching the video. I hope this made sense. If it didn't, leave a comment. Maybe I'll see it, maybe I won't. But enjoy the rest of your day and good luck on exams.